Long time no see. This is the amateur logician. I hope you all are doing well. A justly famous book I want to briefly explore here is How to Lie with Statistics by Darrel Huff. It's a book that's well written, concise, funny, and has great illustrations in it. If we learn the book's lessons well, then we'll think more clearly and logically when it comes to statistics. In this video, let's preview the 1954 classic book How to Lie with Statistics by Darrel Huff. The secret language of statistics, so appealing in a fact-minded culture, is employed to sensationalize, inflate, confuse, and oversimplify. Elsewhere he writes, the crooks already know these tricks. Honest men must learn them in self-defense. Chapter 1 in the book is the sample with built-in bias. In statistics, we seek to describe features of some group. For example, finding an average of that group. A population represents each and every individual which meets the criteria of a group in question. However, gathering data on the entire population is extremely time-consuming and very costly. It's usually impractical. So instead, we usually have to resort to a sample. That is a subset of that population. That means we need a good sample. It needs to represent that population well in order to make inferences about that population as a whole. A famous example given in the book deals with the 1936 presidential election. It's way too expensive and hard to poll every person. It's not going to happen. So we need a good sample. Literary Digest polled those who had telephones. The sample suggested Landon would win, but in fact Roosevelt won the election. The sample was biased. It was unrepresentative. Those who had telephones tended to be wealthier. It left behind those who were not wealthy, and it thereby missed a large segment of their population. The sample had a built-in bias. The best sample is random. That is, everyone in a population has an equal chance to be in the sample. That's the ideal. It prevents a sample from being biased one way or another. Every member must be equally likely to be selected. Hence, we should always want to know how the sample was formed. Can we trust the statistics given to us? Another lesson we can learn from this book comes from Chapter 2, The Well-Chosen Average. An average can easily give an inflated impression. Averages can be misleading. Combine poor people with an extremely rich person, that extremely rich person will pull the average, what's called the mean, upward. It will appear that people in a neighborhood will have more money than they really do. Mathematically, you just add up all of the individual scores and then afterward divide that sum by the total number of cases present. That's the mean. The mean is very sensitive to outliers. But the median, the score that cuts a given distribution of data in half, the middle number, so to speak, often is a better measure than the mean. It's not sensitive to an outlier and is thereby often a better type of central tendency measure. It's best to use when considering household income in a neighborhood, or, for example, home prices in a neighborhood. We also have the mode. The mode is the score or response that appears most frequently. That sometimes is even better. For example, in determining the wage most people get at a given company, the mode might be the way to measure what's going on there. Now, sometimes the mean, median, and mode line up and you get a so-called normal distribution. That's the graph in the middle. It's symmetrical. 50% of the data is to the left and 50% of the data is to the right. Human height approximately forms a normal distribution, also known as a bell curve or Gaussian distribution. Income distribution is not like this, for example. We'll get a skewed graph. The mean is different than the median. Consider the leftmost graph. It has a positive skew. The mean is greater than the median. Most of the data is concentrated on the left side with a few high-value outliers pulling the mean to the right. Sooner or later, by the operation of chance, Huff writes in Chapter 3, a test group is going to show a big improvement worthy of a headline and perhaps a whole advertising campaign, end quote. We have the problem of inadequate samples. Just by chance, a small test group can show a big improvement, and that becomes worthy of a headline or an advertising campaign. Think of quickly rushed medicines or vaccines or a quack supplement that someone is trying to have you buy. We need a large, varied, and random sample. Flip a coin a few times. It won't likely be 50% heads and 50% tails. But do it a lot of times, and then it will approach that 50-50. Here we have science proves that tossed pennies come up heads 80% of the time. That's not a good sample. We have an inadequate sample. Rather than being confused, tricked, or fooled, know the degree of significance. Let's really look at what we're being told. What's the degree of significance that goes with the inference we're being told is the case? Then we can be more sure that the figure given to us is the real deal, an accurate representation, not just something due to chance, like a coin that lands mostly on tails by mere chance, by mere luck. In Huff's little book, he gives us the advice to accept nothing less than a 5% level of significance, often denoted by the Greek letter alpha. Other things being equal, there's a 5% risk that what's given to us is wrong. Inferential statistics is like a court case, innocent until proven guilty. It's too easy to jump to big conclusions that are not warranted, or to make something big out of something that's really small or actually totally insignificant. Huff gives us warnings to this effect with several examples. We have to be careful. We have to be logical in statistics. Data is often in ranges. In statistics, most especially, there's a range based on the standard error. There's a variability or dispersion of a sample statistic from the true population parameter. Or take a simpler example of someone's specific IQ. Let's say it's 101 plus or minus 3. Another person's might be 98 plus or minus 3. Whose IQ is higher? Can you really say? We cannot turn that 101 into something more than it is, given the range. Huff gives the example of old gold cigarettes. Data suggested that it was the least bad or poisonous of the cigarettes. There were ads galore announcing this, but the difference was totally insignificant. It was so small to be insignificant compared to the competitors. Yet that didn't stop the company to proclaim how much better they are, or were. We are visual creatures. We like graphs. Yet they can be misused and abused. Chapter 5 of Huff's book is on the gee whiz graph. Now, if we want to think and reason more logically about data and statistics, one thing we need to be able to do is to judge and evaluate graphs, to spot good graphs from bad graphs. A good graph illuminates reality. In a manner of speaking, it makes us see things better. It helps us understand things better. A bad graph distorts. It can give us a false impression of what's happening. This ability to spot bad graphs is an essential skill to develop, and Huff's book helps us with this. Consider, for example, truncating the y-axis, that is, not starting at 0. That can falsely make a small difference look huge. It can turn a small difference and make it look like it's a big difference, but it's really not. Or consider changing the proportion, that is, having distorted intervals. But that can make data that's roughly flat make it falsely appear to be falling or rising. Or consider a cherry-picked time period. Well, that shields us from seeing the full picture, and that can easily give us a false impression. And if we cannot read the y-axis or x-axis, if we don't know what those represent, how can we really know what we're looking at? How can we interpret it? Huff writes, quote, "A bar chart is capable of deceit. Look with suspicion on any version in which the bars change their widths as well as their lengths while representing a single factor, or in which they picture three-dimensional objects, the volumes of which are not easy to compare." End quote. For a simple example, we can take a line segment and double its length without a problem. But if we're going to represent a doubling of length and width, then the area is going to do more than double, obviously. It will look 4 times as large. So we can distort things very easily. Recall what I said. Statistics is like a courtroom case. Practicing good statistics is like that. And it becomes evident when you read this book's many examples. 27% of a large sample of eminent physicians smoke throaties. Well, so what? What does that really prove? Is it self-evidently true that physicians will smoke better stuff? This juice extractor extracts 26% more juice as proved by laboratory tests. Okay, 26% more than what? Compared to other extractors? Which ones? Old ones from a long time ago? The latest ones from competitors? We don't know. More people were killed by airplanes last year than in 1910. Okay, other things being equal? We seem to be comparing, so to speak, apples and oranges. More people fly now than in the past, so more people die these days than before, but that doesn't mean there's a greater percentage. The percentage might even be less. Another important topic covered in the book is the famous post hoc fallacy. Just because B follows A in time doesn't necessarily mean that A caused B. A may be prior to B, but that doesn't mean it's the cause. There might be a third factor, C, that caused both A and B. And sometimes there is indeed a real correlation between the two, but no cause and effect relation whatsoever. Correlation between two things doesn't necessarily entail any causality between those two things. We have to be careful not to confuse a statistical correlation with any claim that one thing actually caused another thing. Now, Huff gives a very interesting example, a controversial example to make us think about cause and effect relations and not to immediately infer that they exist just based on correlations. Now, there are studies that show if you attend college, you will probably earn more money. But Huff actually challenges this. He makes us think more critically on this topic. He writes, "This unwarranted conclusion has for its basis the equally unwarranted assumption that since college-trained folks make more money, they make it because they went to college." End quote. Okay, that might be the case. It's reasonable. Nonetheless, maybe people who go to college tend to make more money regardless. That's not logically ruled out here. They're just naturally more drawn to go to college. Maybe, just maybe, some of them would have made even more money if they didn't go to college. To be sure, if you get an engineering degree, you might make more money than you otherwise would. Still, we cannot generalize with that case. But Huff wants us to think critically here. It's too easy to be a demagogue, especially on a topic like this, or let the emotions speak louder than logic. Now, as an aside, there's actually an interesting new book, compared to Huff's book, it's very recent, by Professor Brian Kaplan called The Case Against Education, and that arguably overturns a lot of conventional wisdom on the topic of higher education. Regardless, it's not an easy topic. It's hard to disentangle things or be able to filter, comprehend, and interpret statistical data. Being able to find cause and effect relations is not easy. It's very, very difficult. In any case, regardless, I think Huff is successful in helping us think more critically if we follow his advice. Huff wants us to ask critical questions. When we're given some statistics, we should ask questions to help us determine their probable reliability. We cannot take things at face value. We should ask questions like, who says so? How does he know? What's missing? Is anything missing? Did somebody change the subject, which often happens? In a course of argument, the argument's about X, but someone subtly changes it to Y. But Y and X are not identical. And of course, does it make sense? These are the questions we need to ask. This has been a short presentation, a short review of Huff's justly famous book, How to Lie with Statistics. I'm the Amateur Logician. You can visit my website at amateurlogician.com. You can support my work. If you enjoyed this video, please consider buying me a cup of coffee at buymeacoffee.com/amateurlogician. Incidentally, see my entry on causal and inductive fallacies to learn more about statistical fallacies, including p-hacking.